Hello, everyone. Come on in. Feel free to ask me questions while we wait for the rest of the class and for class to start. Got 5 minutes till class starts, according to the norm. I know we should have test 6 up pretty soon, and I will put it up this week. Uh, Maybe I'll make it due. Definitely, I'll make it due no earlier than Sunday, but I might even make it due a couple days later or something like that. But make sure you get that done. When I post it, I'll send an announcement to everyone when and if I post it. I do plan to post it. So
Professor, are you going to post the chapter tests that we could practice, like the
oh,
individual chapter tests?
yeah, am I past due on that? Let me see. Yeah, it looks like I am.
The
Yeah,
last
I'll
one was
put
chapter
chapter
8.
8. Yeah, I'll put up chapters 9, 10, 11, and 36 because we're gonna knock out relativity today. I'm doing a
Okay, thank you.
No problem. I'm doing a shortened version of what I normally do for relativity. I normally do all the derivations and stuff like that, but I think it's good enough for you to either read the derivations in the book or look at my derivations that I did actually on my YouTube channel. You can just do a search in my YouTube channel for derivation, Derivatation. Uh, so feel free to do that. But the main thing is I'm going to give you sort of the crux of what came from the principles of relativity. Of course, I'll tell you the principles of relativity. I'm going to give you the fundamental equations that we use. Again, not deriving them, but then I'll work some problems so you can see how they work and give you some names for quantities, and even give you some hints of other things to look at. Special relativity is kind of fun. It's neat. People generally like it. You can also look up my twin paradox. I think I have a video on the twin paradox, and I think I have a video on the ladder and the barn paradox. I may even have uh, the spinning disk paradox. I'm not sure if that's there. We got more students coming. Still got about 3 minutes. Anybody else have any other questions? I don't have. I usually use a sort of wax type product for my beard, and I haven't done it today because I was sick all day. Now my beard's all standing up looking crazy. Not only that, this left right mirror is driving me crazy. This should be over there. Not where it's at. Actually, no, it should be. Yeah, right here. Nope, nope, right here. Right here. That's where that should be. Smells like pepper. These are the things that go through this brilliant mind. Still got 2 more minutes. It's always going to be the instant where I go to connect my share my screen. That's not going to work. Let's see if I do that now. Share screen, iPhone, iPad. Looks like it's working. Let's see. It is. It is working. That's a good thing. That looks pretty good to me. Stop sharing. Admit another student. All right, one more minute, folks. Crap, I finished my coffee. All right, got about 15 of you. That's pretty good. It's time to start. So we've now finished chapters 1 through 11. We are having a test on chapters 9 and 10. Sometimes I'll make the next one 3 chapters, so it might be 11, 36, and I think we go to 14 next. But either way, we're definitely going to have a test that posts this week, and that test should cover 9 and 10, but it actually might also be 9, 10, 11. I'm not sure yet. Anyways, the main thing is it's going to be an online test. Currently, I would shoot for it being posted sometime today or tomorrow and be due on Sunday. But I'm also going to post the practice for the individual chapters because I have heard some students like that or use that. So I'll make sure that's done. And I might make the due date later than Sunday, but you should really try to get it knocked out by Sunday. There might, in fact, be a second online test that I post this week. That one wouldn't be due on Sunday. That'd be due at least no later than Wednesday, and but possibly even the following Sunday. But the main thing is we're getting near the end of the semester, so the tests actually stack up. So what we did in chapters 10 and 11, of course, were about collisions, and then 11 was about rotational motion, specifically the dynamics of rotation. So we had a equivalent of Newton's second law, which said the summation of the torques is either equal to I, the moment of inertia, times omega, where omega is, or excuse me, times alpha, where alpha is the angular acceleration. We talked about how to derive moments of inertia. We calculated them, all that sort of stuff. Now we're jumping to 36, which is basically now that we have sort of all the major parts of mechanics out of the way, it's a good time to cover relativity because relativity has an answer for basically all those things, but in some cases they differ slightly. So for instance, kinetic energy is no longer going to be 1/2 mv squared. It will in one sense, specifically it will in the sense that as long as we're doing speeds that are less than 1% or even maybe even on the order of 5% or lower of the speed of light, then chances are you're fine. You don't need to use relativity. But the neat thing is, even if you use relativity, it still will, in the case of dealing with lower speed objects, it'll still give you the right answer. In other words, it'll come out, even though the formula is different, it'll come out as 1/2 mv squared, or at least numerically equivalent. So that's kind of interesting by itself. But that's sort of what we decided. I say we, really it was probably Bohr more than anybody, that basically said, hey, if you're going to offer a new paradigm of thought or a new branch of science, it better reduce, at least in the appropriate limits, it better reduce to the old science that worked for so many years. So for instance, if we're covering gravity, we know Newton's laws of motion with Newton's law of gravity was really good enough for us to figure out how the planets orbit. It's technically good enough to get us to the moon, stuff like that. But in reality, there is a little bit of problem even getting to the moon or even communicate with satellites, in that you have to take into account special relativity. But if you're going to say general relativity now or special relativity as well are going to cover the same areas of physics that Newtonian physics did before, they better show the exact same results as Newtonian physics did in that realm of Newtonian physics. So that's basically a postulate that Bohr helped and decided on us using when they were coming up with with quantum mechanics. So it's a good thing. Anybody have any questions before we get cracking on this next thing, relativity? All right. Somebody has their speaker or their microphone not muted. I'm trying to look for the person because we hear you coughing and or blowing your nose or something. Maybe that's it. I just found one that was not muted, so I muted it. Sorry if that was aggravating for someone. But anyways, so special relativity is kind of interesting one. It's one of my areas that I really liked in physics. I majored, did my undergraduate thesis in general relativity, and I did my master's just by luck of fate. I did it in chaos theory specifically because I was a little bit interested in chaos, not very much at all, really, to be honest with you. But my advisor had been doing stuff, and he told me how to do something. So I went and did something. I just happened to literally, like, even before my first day, technically as a grad student, I found something no one had found before, and because of that, I already had my thesis basically done even before grad school started. So I was able to finish my master's in a year. So that's why I did chaos theory as opposed to general relativity or something like that. But then I went for my PhD work. I did general relativity, and specifically we were working on the grand challenge, which was this big bunch of grants that the NSF had made for us to try to predict what would happen if two black holes collided. And we wanted to do that as theorists before the experimental apparatus was online, because theorists really, if they're worth anything, should be able to predict results before we actually have them, as opposed to patching them up after the fact. And lo and behold, I say lo and behold, the funny thing is we had a bunch of different schools: University of Illinois, Urbana-Champaign. We had UNC Chapel Hill, which I was at. We had Penn State, I think Cornell as well, and NYU. A couple other schools were involved. And we were all writing code, figuring out boundary conditions, rewriting Einstein's equations in forms that my PhD advisor, Dr. James York, had worked out with Madame Choquet-Bruhat, and I think Dr. DeWitt as well worked on that. But that was sort of what made him famous, was he discovered a process by which people were mostly ignoring, and was able to transform the Einstein's equations into a form that was a little more reasonable, hyperbolic versus elliptical differential equations. But anyways, we were working on that, and everybody was doing great things. We were getting publications just from the work being done, even though we hadn't completely created a model yet. And this one lone grad student, I think at Harvard or Princeton, by himself solved it and published the actual solution before our big grants were finished. So he wrote his ticket, and I don't know his name, sadly, but that's kind of interesting. I had seen that there were some issues going on, so I had took a job just to make sure, because I wasn't sure my advisor would be there. Sure enough, my advisor left everybody. So anyways, I still love general relativity, so we're going to talk about special relativity today. General relativity means in general, where special relativity covers a special case of where we're basically cutting out gravity. It doesn't necessarily sound like it, but that's really the big goal. So the postulates of relativity are: the laws of physics are the same for all inertial observers. What do we mean by inertial observers? Well, believe it or not, that actually takes out gravity, but it does other things. So for instance, if you took and mounted a camera over top of a merry-go-round, say, or one of those spinning discs that you see in playgrounds, and you mounted it so that the camera looked down and could only see the disc, then you can't tell from that camera footage, since you're mounting it to the device and therefore there's no relative motion of it in the camera, you can't tell if the thing's rotating or not. But here's the weird thing: if you stick a basketball dead center on that disc, it's not going to be perfectly centered. It's not going to be perfectly balanced. So if it's actually spinning, you will see something that looks like magic. Specifically, you'll see a basketball that spontaneously goes from not moving at all to some velocity and actually speeds up and flies out of the screen. That would be one that appears to violate Newton's first law of motion, which is also called Galileo's law of inertia, and therefore it's a non-inertial reference frame. In that case, you know what's really going on, because I told you how it happened. But basically, the thing was a little off-centered, and it was actually just trying to obey Newton's first law by not changing its motion. And its motion was associated with the very motion of the spinning disk, which was just rotation like that. As it moved outside, then it was orbiting sort of the center, but friction and rolling all combined to make it just shoot off whatever its last direction was going, it was going at the instant it got to the edge of the actual merry-go-round. So that's what happened. But that would not be an inertial reference frame. Similarly, if you just look at a chunk of the sky and you see a balloon falling or a bird falling or a stick falling, you would see something with no obvious force acting on it, specifically the bird, the stick, or the balloon, or whatever it is, the ball. You would see that moving as if it had a force acting on it. And since we can't see the force, that is what we call a non-inertial reference frame. So in fact, you should look for frames that are inertial. And once you find a frame that's inertial, any other frame moving in uniform velocity, meaning a constant magnitude of velocity and a constant direction of velocity, any other frame moving like that will also be an inertial frame. If you want more details, this is probably the best book you can get to understand that. I mean, there's a lot of other good books, but this one sort of just really is using the brilliance of fine teachers like John Archibald Wheeler and Edwin Taylor, both of which were two of the 3 to 6 authors of, quote unquote, the Bible of general relativity, a big black book called Gravitation. But anyways, that's a great book, and I'm reading it for the 5th time now. But anyways, so that's the first principle of relativity. The laws of physics are the same for all inertial observers. When we go from that to general relativity, the difference is going to be the laws of physics are the same for all observers, period. In other words, Einstein works out what we're missing and no longer has to have inertial reference frames. Now, the second principle of relativity, and your book says all this, so don't feel too bad if you're not writing it down quick enough or I'm not saying it often enough. But the second principle is that the speed of light is a constant, independent of the motion of the source and independent of the motion of the observer. That is the second law. And that's a really weird one. As well as I do, if I can throw, say, 60 miles per hour, throw a ball 60 miles per hour, and I get on the back of a flatbed Mack truck, and the Mack truck's going 60 miles per hour, that means if we could ignore all the bumps and the roads curving and stuff like that, and going uphill and downhill, slowing down, speeding up, traffic, all that stuff, if we could ignore all that, in 1 hour, any particular spot on that truck, including the spot that would be right under my feet on the flatbed trailer, would move, in fact, 60 miles. So it just moves, say, left to right, 60 miles or whatever. Additionally, if you were able to do that and follow the ball, what you'd see is when I threw the ball in the same direction as a truck, the ball over a 1 hour period, again, assuming the ball's not going to hit the truck, it's not going to change speed or anything like that, but assuming the ball just keeps going, we would see the ball move 60 miles with respect to that space on the flatbed right under my feet. So in fact, it would move 60 miles relative to that space on my feet, but that space on my feet had already moved 60 miles itself. So that would mean in that 1 hour, the ball moved 60 plus 60 or 120 miles. And therefore the velocity must be 120 miles per hour. That is a very typical thing that we all understand, but it turns out it's just not right. At least regarding the speed of light, and at least regarding things approaching the speed of light. I will give you the formula of how those velocities add. Galilean relativity says basically that the velocity of A with respect to C is equal to the velocity of A with respect to B plus the velocity of B with respect to C. Notice how the last subscript in the first letter, VAB, and the first letter in the second symbol, VBC, match. And also notice that the first symbol in the first subscript in the first symbol and the last subscript in the last symbol actually match the symbols on the subscript for the left-hand side. So VAC is equal to VAB plus VBC. I'll write that later. You've already seen it, and I've already given you an example during this lecture on how the special relativity equation works. So you've even seen that before. But that's just straight Galilean relativity and stuff like that. And here we're going to jump to special relativity. And I'm going to start off just by listing sort of the ramifications of this and then solve some problems with it. So let's get started. We know our laws of physics now, our principle of special relativity, if you will. The principle of special relativity is, in fact, one, laws of physics are the same for all inertial observers, and two, the speed of light is a constant independent of the motion of the source and independent of the motion of the observer. Now, all of that came from something specific, so I'm going to give you a little bit of the history. I prefer not to give you any, to be honest with you, just so we can work problems, but I can't just not tell the story. It's kind of neat. So the story, or part of the story, is that when Maxwell had discovered that his equations, which you guys will study in 242, could be put together in such a way that they make a wave equation, he looked in the spot of the form of this wave equation, which is really anything with a second order derivative of it in space, like second derivative of the electric field with respect to x squared. That is a derivative in the in space, d by dx, in other words. But this one's d2e over d2x, or dx squared. That's one side of a wave equation. Then the other side of a wave equation has, of course, the equal separating it from the other one, but it has 1 over the velocity squared, and then a second order derivative of that same thing, which I said e earlier, but this one's in time, so it'd be the second derivative of e with respect to t. That's the form of a wave equation. And when Maxwell put his equations together, he was able to find such a wave equation. And he looked in that slot where the velocity goes, and lo and behold, it was basically the velocity had to be 1 over the square root of mu 0 times epsilon 0, which mu 0 is a constant related to gravitational fields, and epsilon 0 is a constant related to electric fields. And lo and behold, when you multiply them, take the square root, flip it over, you got exactly the speed of light. So, Maxwell's like, oh, crap, I know what light is. So that was a really big deal. But we had seen waves. We'd seen ocean waves. We'd seen sound waves. And, it really takes an ocean to make a sea wave, or a pond to make a water wave, or air to make sound. You literally have to compress the molecules against each other to make an area of compaction, and then an area of rarefaction right behind it, and then an area of contraction, so on and so forth, compaction, so on and so forth. So it seemed reasonable that waves need a medium to travel through. So we hypothesized the existence of something called the ether, and the ether was supposed to be through all space. And then we set about looking for it. So what we did was we shot a beam of light one way, let it go through a half silvered mirror, so it would break in half and go that way and that way. That would bounce off a very precisely created arm, and this one going this way would also very precisely be created, such that the lengths were exactly the same. That split beam would bounce off the two mirrors, come back together, and then go to our eyepiece, which is what we were looking at. And if there was say a quarter wavelength difference, then a sine wave trying to line up with a cosine wave would actually make a zero wave. And if that happened, we know that the difference in travel was basically half a quarter of a wavelength. And that would be due to basically the velocity of the Earth going through the ether in the direction that the ether was moving would actually speed it up when it's going along it, or slow it down when it's going against it. And that would be how we detect our velocity through the ether. And we could take and turn it 90 degrees and make sure we get the other one. And we could turn it vertically, even another 90 degrees. And we did this experiment very precisely. We knew exactly how precisely we need to do it to predict, or to actually see the data with the apparatus we had. So we had an apparatus that worked. And it was a Michelson-Morley experiment with interferometry. That device is called an interferometer. And it gave us a null result, meaning it basically showed that the light always came back completely in phase with each other, as if there was no velocity relative to the ether in any direction. And we did many experiments. So by 1890, Lorentz and some other people had worked out some details to try to save the ether. And they conjectured, for instance, that perhaps matter compresses along the length of its motion as a result of the ether, and it compresses by a factor that we'll call gamma, and we'll see in a second. Nobody liked that, but it did explain the results, so it was kind of nice. And we to this day call the transformations the Lorentz transformations, even though they're really ultimately were accepted when we based them on the special theory of relativity, which Einstein proposed. Einstein proposed this in a problem with physics that didn't even exist. In other words, he saw a problem not only that no one could solve, but that no one necessarily existed in relativity, and to some extent with special relativity, other than the interferometry thing. So in the 1890s, they were battling this interferometry thing. In 1905, Einstein published like 6 or 7 papers. Every one could have won him the Nobel Prize. One of them did, the photoelectric effect paper. But one of them was special relativity. And what Einstein had done is he looked at that wave equation that Maxwell had put together and realized that when you change to a frame moving at some velocity relative to some other reference frame, and I literally mean like a coordinate system here, like we imagine one coordinate system's my office, and this is like the x-axis and this is the y-axis, that's my office, right? But here's another reference frame flying by at say 100 miles per hour, and if you jump to that reference frame, you'd expect the speed of the wave to speed up by 100 if they happen to go the same way, or to slow down by 100 if they happen to go opposite ways. But Einstein found none of this happening from Maxwell's equations. So he really took that as a statement saying, hey, light doesn't change its speed. And he saw these paradoxes that came up if you didn't predict that. So ultimately he used that. And then he used these neat, what he called Gedanken, which is German for sort of a thought experiment, to come up with results that I'm getting ready to give you now. So that is where special relativity came from. And to date, it is the most tested theory in the history of mankind. And it's been tested literally on the orders of thousands of times per second, thousands of times per year, thousands of times in some cases per day, and never once been found to be in error. So the special theory of relativity is really well tested, and we do not expect it to be overturned in any serious way anytime soon. And even if it did, according to the correspondence principle, which is what Bohr had told us, which I talked to you about earlier, it still has to reduce down to special relativity in the realms where special relativity works. So we're pretty confident about this. So let me go ahead and share the screen so I can give you some symbols and some terminology and stuff like that. So with special relativity, first off, we have now defined the meter and the second in such a way that the speed of light is now perfectly known. So we say that the speed of light, which we give the symbol c, so speed, that's the worst looking thing ever. The speed of light equals c, and it's now exactly 299,792,458.0 with a bar over it meters per second. So that's the speed of light. We know, in fact, that there's some handy ways of thinking about the speed of light. One of them is using a symbol called beta. So here's the beta symbol, and that is defined to be V over C. And as example, let's say, for instance, the speed of sound, which is about 330 meters per second. And that's actually a function of temperature. So it's not, really, I'd have to probably put another number in the ones place and another number in the tens place, to be honest with you. But this is just give you an idea of it. Now what we're going to do is take and divide that by 299,792,458 meters per second. And when you do that, you'll get this beta, which is also considered sort of a fraction of the speed of light. So 330 divided by 299,792,458, 299.792.458 gives me 0. Well, I'd like to write it with all the decimals, but it's really so small. I'm going to say 1.10, 1.101 times 10 to the negative 6, which also is 0.000001101. So you can see it's a very, very, very small number. And of course, when you get less than 0.1, maybe even less than just 0.5, or excuse me, 0.05 and 0.01, you probably don't need to use relativity. Okay, so that's one symbol. Another
This is to find the speed of sound.
This was the speed of sound relative to the speed of light. So one of the common variables that we use in relativity is this beta, which I want you to think whenever you see the symbol beta, I want you to immediately think, oh, divide the velocity by the speed of light. So it comes up with a dimensionless quantity. Notice it has no units. I didn't forget to write them. It's literally no units. That makes sense? You could, by the way, call it meters per meter if you wanted, or seconds per second, or anything like that, to be honest with you, because that's what's really happening as the units are canceling out. Another symbol that comes in handy in relativity is called gamma. So I wanted to show you what that is. That's the Greek symbol gamma, and it is 1 over the square root of 1 minus v over c squared, which you see is in fact that beta that we talked about earlier. So that's 1 over the square root of 1 minus beta squared. So that's another number that comes in handy. So that is gamma. And notice this quantity, gamma, is greater than or equal to 1. Okay. So for instance, here's another example. One, I'm going to say gamma for sound, is equal to 1 divided by the square root of 1 minus 1.101 times 10 to the negative 6 squared. So when I do that, I think what you can see is if I square 1.01 times 10 to the negative 6, I get 1.212 times 10 to the negative 12. So it'd be 1 over the square root of 1 minus 1.212 times 10 to the negative 12th. And if you subtract that from 1, you're obviously going to get a very, very, very small number. And then you take the square root of that and you basically get that's approximately 1. What you could do, though, is you could use the binomial theorem, which basically says 1 plus or minus n, or excuse me, 1 plus or minus x raised to the n power is approximately 1 plus or minus n times x. And then it's got a lot of other terms, but we can do that here and say that gamma for the sound is approximately equal to, notice our function is in fact 1 times, let me double check this. Hold on, I want to make sure I don't grab the wrong symbol here. I also want to shrink that a little bit. Nope, I don't want to shrink it like that. Hold on, double checking my work here. Yeah, it is 1 plus or minus. Okay, so what I'm actually doing is saying that gamma is equal to 1 minus beta squared raised to the negative 1/2 power. So that's really what I'm doing. So now using that expansion that I got, which is just a Maclaurin series expansion or whatever, this is going to be 1 plus or minus. Oops, I should probably write it in red. It's going to be 1. Now, in this case, it's plus or minus, and we see ours in the black writing is minus. So I'm going to do minus. And then I'm going to take x, which is beta squared. So I'm going to say 1.212 times 10 to the negative 12. Notice that was already beta squared. That's what I put here. Okay, so that's actually beta squared. And then I'm going to multiply that times the power, which is negative 1/2. Again, I should be writing in red. So I did it a little bit in the opposite order, but you can see, in fact, this is going to be 1 plus 0.5 times 1.2116. That is 1 plus 0.000000000. Now we're up to 9, 10, 11, 12, 6, 0, 5, 8. Okay, so yes, it's clearly bigger than or equal to 1, but in this case, it really is close to 1. So, and that trick there, that applying this 1 plus or minus x to the n power, that's so important that in the inside cover of your textbook, they give it literally on the inside cover. So that is a expansion that you occasionally use whenever you have anything raised to a power. You can use that, and actually, I think it has the first 3 or 4 terms, but you can pretty quickly figure out the pattern to get 12 terms if you want. Any questions on that?
Why did you make the power 1/2?
Because it was a square root.
Oh, never mind. Yeah, I feel dumb now.
Oh, that's okay. No, everybody misses that. It's cool. So yeah, perfectly normal. All right. So now you've seen this. What I'll give you now is another example. Let's say
So the exponent just cancels on it though?
Well, what happens is when you actually do a Taylor series or a Maclaurin series expansion on this 1 plus or minus x to the n, the first term is 1. The second term is plus or minus the power of the whole thing raised, which in this case was negative 1/2, and then times whatever came after the plus or minus. So that's where all that went. So for instance, if we took this speed, which I think you might realize is pretty close to 2/3 of the speed of light, let's say 2.00 times 10 to the 8th meters per second. That really is the 2 instead of 3 times 10 to the 8th, because we often will use C as approximately, I think you can see 3.00 times 10 to the 8th meters per second. You don't always have to have all those digits, and I think you do see that it does round to 3.00 times 10 to the 8th. So if we see that, then this means beta can be calculated. What is beta and what is gamma is really what I'm saying there. So beta, we can see, is approximately 2.00 times 10 to the 8th meters per second over 3.00 times 10 to the 8th meters per second. Again, I could have used the other one, but really, if I'm only given 3 sig figs, why should I use more than 3 sig figs? Because I have to round that anyways. So in this case, we get basically 2/3, which equals 0.667. So that's one answer. Now, what is in fact gamma? Well, in this case, gamma is equal to 1 over the square root of 1 minus beta squared. So gamma in this case is going to be equal to 1 over 1 minus 2/3 squared, which equals 1 over the square root of 1 minus 4/9. Notice 1 is 9/9, so 9/9 minus 4/9 is 5/9. So we get 1 over the square root of 5/9, which actually equals 3 over the square root of 5. And you can tell since 2 squared is 4 and 3 squared is 9, clearly square root of 5 is smaller than 3. So we can tell already that that is in fact greater than 1. I will compute it just for the heck of it. 3 divided by square root of 5 is approximately equal to 1.34. And I'll carry one extra sig fig just for the heck of it. So I'll say 342. So again, we do see that beta is in fact, or excuse me, that gamma is in fact 1 or larger. And you can see also that when I had something that was appreciable fraction of the speed of light, I got a appreciable number for the gamma. And in fact, a lot of physics can be done just by sort of memorizing what gamma is for various speeds beta. Okay, so like what I often do, and I was going to do it in this class, but my Excel was taking forever to crank up. But you can create a column where you basically compute what gamma is for, or excuse me, what beta is for gamma equals 2, gamma equals 3, 4, 5, 6, 7, 8, 9, 10, 100. You might do 500, you might do 1,000, 10,000, 100,000, and you can just solve the expression or the definition for gamma in terms of that. So let me box off these important results. Beta equals 1 over C, or excuse me, V over C, and gamma is equal to 1 over the square root of 1 minus beta squared, and gamma is always greater than or equal to 1. So we've now seen some incidents that involve that, but we haven't really, I haven't shown you anything about how that comes into play or why those numbers are even remotely important. But one thing we can do, for instance, if you want to find out what gamma is, you can say gamma is equal to 1 over the square root of 1 minus beta squared. So if you do want to make that spreadsheet like I suggested, you would need to be able to find beta for a given gamma, because what you want to do is you want to be able to type in a gamma. Let's say I want this weird relativistic effect to be a factor of 7. So you put in the Excel sheet 7, and what you want spit out is beta, and you might even want beta and the speed of light multiplied so that you can get the actual velocity in meters per second. You might even put another column that can convert it to miles per hour. For instance, the speed of light in miles is actually 186,000 miles per second. So that gives you another idea. Also, the speed of light is fast enough to go around the equator of our Earth about 8 times in a single second. It can make it about 5/6 of the way, or it might be 4/5, somewhere like that. Yeah, about 4/5 of the way to the moon in 1 second. So obviously, the speed of light is such that the light we're seeing bouncing off the moon's surface gets to us about 1.2 seconds after it left. So what I'm going to do now is show you how to solve this for beta. So I'm going to square both sides. I get gamma squared equals 1 over 1 minus beta squared, which becomes 1 minus beta squared equals 1 over gamma, which becomes beta is equal to 1 minus 1 over gamma times, or excuse me, square root of all of that. Now you could also say this is equal to the square root of gamma over gamma minus 1 over gamma. And in this case, it'd be gamma Oh no, it'd be like that. Sorry about that. Let me erase that last bit. Let me just do this. There you go. That's easy enough. So we can do that. Whoa, I just erased something back soon. So I can make the 1 gamma over gamma, and then you just get the square root of gamma minus 1 over gamma. So that's another way you can manipulate it. You can commit this to memory if you want to. I really don't think you need to, but if you have any problems doing that level of algebra, then you probably should. So now let me show you exactly why that's relevant. So it turns out that you can do these quote unquote thought experiments, or Gedankens as Einstein called it. Let me stop sharing for a second. You can do these thought experiments in such a way that you can get results that help you understand how nature behaves. For instance, you can imagine, like your book does, 2 train cars. 2 train cars happen to be at one instant in time perfectly aligned, so the front edge of this train car is lined up with the front edge of that train car, and the back edge of this train car seems to be lined up with the back edge of this train car. And at one instant, at that very instant, in fact, the train car closest to us is moving this way at some large fraction of the speed of light. But what happens is automatically there's these little feelers sticking out from the other train car. And as soon as it touches those, in the center of both of those train cars, there's a light that turns on instantly. Now, because it turns on instantly, what that means is instantly a light comes on in the center of the train car farthest away, the one that's sitting still, and they both leave as the light bulb turns on. You can imagine the light from the light bulb shooting towards the front of that train car and shooting towards the back of that train car. That's not in motion. So in fact, it would see, if you happen to be in that train, you would see this light beam hit the front at the exact same instant this light beam hit the back. That's in that sitting still train. But in the train that was moving, what you'd see is, boom, the light came on, and then the light would in fact get to the back first because the back of the train is coming towards it and the front of the train is moving away from it. So in that train, you would actually say that the 2 events were not simultaneous because the light got to the back first and then got to the second, and then got to the front. So that's one of the many thought experiments you can do. And that one, you're actually showing that simultaneity is now relative. So that's one of the results. Simultaneity is relative. What one person finds in their coordinate system as being 2 events that happen at the exact same point in time are not necessarily simultaneous in another frame that happens to be moving at some velocity with respect to it. So simultaneity is not a universal property that can be applied to every reference frame. That's crazy. Another one is you can do the same thing and make a light clock where basically at the bottom of the train car is this flashlight, and this flashlight lets out 1 photon of light, which is a particle that would say exists that actually carries or is light. That photon will shoot out of that flashlight, bounce off the mirror above it, and then come straight back down. And that would be what we call a click of time. Maybe that's the unit that we wish to use. You could actually work it out in seconds if you want by just dividing twice the length by the speed of light, and that would give you the actual time. But it's a perfectly reasonable unit of time to use. Now, if you had watched this train car go by you, then what you saw was the beam of light shooting from the back edge of the train car. And since the train car is moving this way, you saw that beam of light come all the way over to here and boom, hit the mirror at the top of the train car way over here, and then come all the way back down and come back to the flashlight down there. So us on the side of the track says the light beam took this path, and we could calculate that time, and we get an entirely different time from the person that's sitting right there next to the clock that said the light beam went straight up and straight down. So that's another ramification of relativity, that length is not a fundamental quantity such that you can say something's 3 meters and everybody will agree it's 3 meters. No, in fact, it's physically going to change. If you're riding with it, or let's say you're measuring your actual car while riding in it, you take the tape measure. Don't do this, by the way. Obviously, this is not a safe thing. But if you're driving with your car and you take a tape measure and you stretch it from the very front end to the very back end and you measure it, that's something we call the proper length, because in that frame, and proper is not really a good word for it. It just is our version, our English version of the word that Einstein used, which is a much better one and means something slightly different, but like appropriate maybe. But anyways, are legible or something weird like that. But anyways, that's the proper length. Now, if we measured that here from the side, as the car blew by, if that car was actually measured to have a proper length of say 4 meters, which is about 17 feet or something like that, we might actually find that it's going to be 2 meters. If it's going fast enough, it literally can shrink down to 2 meters. Of course, that would be a gamma factor of 2. And hence, I'm going to show you that stuff. So we've got simultaneity is not universal. So there's one ramification. Special relativity.
Are you sharing your screen?
Not yet. Thank you for reminding me. There you go. So special relativity. The laws of physics are the same for all inertial observers. That's the first principle. The second principle is the speed of light is a constant, independent of the motion of the source and independent of the motion of the observer. One ramification, simultaneity. Is relative. Again, what you think is simultaneous, another person might not. A great example of that you can see on my YouTube channel is called the ladder in the barn paradox, where basically a boy tries to fit a 20-foot ladder in a 10-foot barn. And in fact, in the father's frame who's watching the boy run with the ladder, it actually works, because what the father sees is the boy running so fast that gamma is equal to 2. The ladder, which was 20 feet, is now 10 foot, and the barn is still 10 foot. So what he sees is the boy run through the door, the front edge of the ladder gets to the back edge of the barn at the same instant as the back edge of the ladder gets to the front edge of the barn. In other words, the door he came through. And he can quickly at that instant close the door. And for that instant in time, the 20-foot ladder fit in the 10-foot barn, according to the father who's not running along with it. Now, the son who was carrying it, in fact, saw an entirely different scenario. In his frame, the barn went from 10 meters wide or 10 feet wide, if depending on what we were using, to in fact 5. So he saw the barn get smaller and the ladder was still the same size. And what he saw was the back edge of the barn was hit by the front edge of the ladder, busted through it. Then the boy comes in, and then the back edge gets lined up with the front edge of the barn, which is where the door is. And the father closed it in completely non-simultaneous event. So in the father's frame, it was simultaneous, and the boy's frame, it was not. So that's one thing we've lost. Now, another ramification of this is time is relative. So time is relative. And I'm going to put a semicolon on that and say time dilation. Do y'all know what dilation means? If you have eyeglasses, you might know what it means, but it means make it get bigger. So if you go to an eye doctor, they want to see the back of your eyeball, and the best way to see the back edge of your eyeball, is to have your pupils dilate. That means open up bigger. So in fact, time gets longer, if you will, for moving objects. What we'd say is moving clocks run slowly. So moving clocks run slowly. And it doesn't matter who you're talking about. If you see a clock moving relative to you, then you know that clock is running slow. But the other person who sees the clock sitting perfectly still with them says your clock is moving slower. And guess what? You're both right. Okay. Then we have a third ramification. And that ramification is length, which I've already mentioned, is relative. And there's something called length contraction. So in this case, moving objects shrink in the direction parallel to their velocity. And that's the only dimension they shrink with. So for instance, a Volkswagen Beetle only gets shorter from bumper to rear bumper, but the height of the Volkswagen Beetle would stay exactly the same. You can see, I'll post some of these videos from my YouTube channel. I'll post them on our module, but I did one where I tried to make a Volkswagen Beetle go so fast, or excuse me, made a Lamborghini go so fast that it looked like a Volkswagen Beetle. One way is by making it the same length, and the other way is by making the windshield at the same angle. So you can do that as well. So those are the first three things that happen, but it turns out momentum's changed. Momentum's changed, kinetic energy's changed. And the famous expression E equals mc squared is introduced. So let me show you these quantities. First off, T, the time, is equal to the proper time times 1 minus V over C squared, which you can automatically see already. This becomes a lot easier if you write this as, let's put a delta there as well, as delta T0 over the square root of 1 minus beta squared. That's one way we can make the writing easier. But another way is we can go ahead and say it's equal to gamma delta T0. I will tell you this quantity right here is called the proper time. And this time is measured by a clock that is not moving. So for instance, when we were talking about that person on the train, the person on the train with the clock, say in the back of the train car, that's basically the flashlight that shoots up, bounces off the mirror and comes back down. To that person riding the train, they can sit down in that train and, you know, even, you know, sit crisscross applesauce with the with the actual flashlight right between their feet, and the flashlight will shoot up and come back down. To them, that clock has not moved, so they're measuring proper time. And for instance, if we discovered that a certain process, let's say making a cookie, took 5 minutes, if we watch that person make a cookie exactly the way they're supposed to, we watching the train car ride by, if they were going fast enough, we could say that in fact the cookie took 10 minutes. Okay, so in other words, her clock appears to be running much slower, which also means her time is dilated. So we see her heart beating as if it had been a whole 10 minutes going by. We see it as if the cookie took a whole 10 minutes to be made. And she would actually say the same thing to us. If she looked back and saw us, she'd say, oh no, I'm not moving to the north at, you know, root 3/4 square root of 6 or times c or something like that. In fact, I see you guys moving the opposite direction at that speed. So I think you making the cookie took 10 minutes, and they're both right. Okay. So that's time dilation. And that's an equation that obviously is something you guys need. I'm trying to, just definitely did not mean to do that. There's another expression, your book derives this as well, and that expression is L is equal to L0. Well, actually, let me write it the way I started before. It's equal to L0, the proper length, times the square root of 1 minus V over C, quantity squared, which I think you can see is L0 times the square root of 1 minus beta squared, which I think you can see is equal to L0 over gamma. All of those are equivalent. And this quantity right here is called the proper length. I could have wrote that a little nicer. Length. And that, of course, is a length measured by someone who doesn't see the object as actually moving. So again, this is like a person getting out of a convertible car on the hood and stretching the tape measure from the front edge to the back edge and measuring it. That would be the proper length. Okay. So that's two of the ramifications, or two of the equations that show the ramifications. The simultaneity can come from the Lorentz transformation. Momentum becomes gamma. Well, actually, again, let's do it this way. Is M times V. Let's say P sub X is M sub V sub X. It gets complicated if it's motion in several dimensions. We're just sort of treating one-dimensional motion. Which I think you can see is gamma MV. Okay, so that's another result. Momentum doesn't behave like momentum unless you put a gamma in front of it. So some people interpret this gamma times M as a relativistic mass. We generally don't like that. Okay, but it does make some sense because it turns out that gamma in front of the M does play a role in the fact that when we try to use Newton's second law of motion, we have to use that momentum. So in order for you to accelerate something up to the speed of light, that gamma forces this the quantity, the force required to become infinite. And that's why we believe that anything with mass cannot travel at the speed of light, because it would have to have an infinite amount of energy put into it and an infinite amount of force. So that's one of the things. Kinetic energy is going to be also changed a little bit. In fact, actually, your book does this derivation, but I'm not going to mess with it. And I don't expect you to know these derivations, by the way. I just want you to understand that they exist. So the energy actually has more than one equation that we're going to deal with. So for instance, one of the equations is this. So E equals P squared, or E squared equals P squared C squared plus MC squared squared. That's the total energy. Whoa. Kinetic energy, K, is actually gamma minus 1 times MC squared. So that's another oddity. And MC squared is the rest energy. And of course, that's another equation. It comes in handy. In fact, that equation explains to us how the sun can live 10 billion years, because it turns out basically you're fusing hydrogen and helium. If you take 4 hydrogen nuclei, which is basically 4 protons, and you make that into 2 protons and 2 neutrons, you'll find out that there's some mass being lost there. There's also some neutrinos that come out that we think are close to massless, and there's some positrons that come out, but they're really small, on the order of 1,200 times smaller than the mass of the protons. But anyway, the total mass difference between 4 protons and what actually comes out, which is a helium nucleus, which is 2 protons and 2 neutrons, and some other little giblets. If you take that mass and multiply it by C squared, that's the energy that that one nuclear reaction gives off. So that's kind of helpful to use as well. There's also an equation that relates to basically the Doppler shift. I'm not going to, it may show up in your homework. It may show up in your practice test. And I think that's fine for you to do on there, but I'm not going to test you on it. So you can ignore that if you'd like, except for the homework, because it always is worthwhile for you to do that in homework and in practice tests. Okay. So those are some of the ramifications and the relevant equations for it. So let me go ahead and show you some questions and how to solve them. Oh, one more thing I got to do. So relativistically speaking, we have Galilean relativity. So let's imagine for a second a coordinate system. Okay, so that's our coordinate system. This is the x-axis. This could be the t-axis, or it could be the y-axis. I'm going to put it as the t-axis right now. And that's not that weird, believe it or not. We sometimes do put t on the vertical axis when we're dealing with relativity. Now we're going to define another coordinate system that is set up in such a way that it happens to go or be lined up perfectly with the xt coordinate system at t equals 0. And that axis is the x prime axis, and that axis is the t prime axis. But like I said, at t equals 0, the x prime axis was laying exactly on top of the x axis, and the t prime axis was laying right on top of the t axis. But the s prime coordinate system, in fact, is moving with a velocity v, so that at time t, so this is all taking place at time t, okay, whatever that means, which by the way, you're going to see there's a t and there's a t prime. But what that means is in this frame, the S frame, actually, I want to use a nice straight line on that one. So in the S frame, the S prime axis has in fact moved a distance VT. Okay. And we wish to know the T prime X prime of this one, but we also wish to know the T and the X of this position as well. Okay. Well, this distance right here is just going to be called X prime. And in fact, what we can say is that X prime, if we were doing Galilean relativity, actually, should I do it? I should say, no, I'll say X. Sorry about that. X, if we were doing Galilean relativity, should be in fact just equal to X prime plus VT. Now, the problem is we actually have to use our T appropriately. So it doesn't make much sense to have an X prime without a T prime, but it's also not obvious to you guys unless you go back over what I said about time being relative, not only in duration, but in simultaneity. I'd have to put this T prime here, but Galilean would have no difference in time and time prime. So this would be perfectly reasonable for Galilean relativity. And he would also say that T is equal to T prime. That's Galilean relativity. Okay. But in reality, Einstein found that X is equal to gamma X prime plus VT prime. And Y is equal to Y prime. And Z is equal to Z prime because the motion's only going along parallel to the x-axis. But get this, T is equal to gamma T prime plus V X prime over C squared. And this is in fact the Lorentz transformations and they are in fact the correct ones. This is relativity. Okay, now that we have those, we can put any, consider any coordinate system and then consider another coordinate system moving with some velocity v relative to it, and we can get the coordinates transferred back and forth. You just have to pay attention when you're working problems to exactly what they're giving you. For instance, one of the problems in the homeworks for chapter 36, they're giving you like, say, T prime, but they're giving you X instead of X prime. So sometimes you might have to use one of the equations to find out what the X prime is so you can have the appropriate symbols for the right-hand side of the equation. Now, if you wanted to switch from this explanation of X, Y, Z, and T to X prime, Y prime, Z prime, T prime, all you have to do is reverse all the symbols from primes to non-primes and all the non-primes to primes, and then replace V with negative V. So if you wanted to convert X prime or X to X prime dot dot dot, you just reverse V with negative V and no prime to prime. So that's pretty much how that works. Now, one more result that I got to give you. Again, we're only treating things as if they're moving parallel to the x-axis. So the other thing I got to give you, and you can derive it, by the way, from those Lorentz equations, but basically what I was telling you earlier was the velocity of object A as seen by object C, Galilean-wise, was supposed to be the velocity of object A as seen by B plus the velocity of object B as seen by C. That's Galilean. But for our case, relativistically speaking, the velocity of A with respect to C is equal to the velocity of A with respect to B plus the velocity of B with respect to C, all that divided by 1 plus velocity of A with respect to B, velocity of B with respect to C over C squared. And as we have in both cases, velocity of IJ is actually exactly equal to the velocity of JI. So you do need to remember that. That comes in very handy. You can look back, I think it was chapter 3, where I actually did some work with this particular problem, with this particular addition of velocities. But that's how velocities add, at least in one dimension with regards to relativity. Any questions on that? Now, I know we haven't done any of the actual problems, so don't feel bad. That's okay. We're getting ready to do them now. So first off, what we're going to do is we're going to consider a muon. So a muon has a life that is quite short. It's actually created in our upper atmosphere when radiation and particles arrive at the outer atmosphere from the sun. That actually causes reactions that create, and these are nuclear reactions that create a particle called the called the muon. They at one time thought the muon was in fact a meson, but it's not. But in doing so, they discovered, of course, that it had a very short life. It lives on the order of microseconds in length, and that because of that, when you see them, they quickly disappear. So I'm trying to look for a specific spot in the book while I'm talking to you. So let me get that real quick. Your book covers the twin paradox. One thing I definitely expect you to know about the twin paradox is that one, it's not a paradox at all, because if it's a paradox, that would be a problem with physics. But two, the paradox is not that the twins are all of a sudden different age. That's what a lot of popular writing says. The paradox is that two twins, one going off on a spaceship to go to see Alpha Centauri and then returning, traveling at say 3/4 the speed of light all the way, will come back and be younger than their twin brother. No, that's just a fact. Okay, that's not a paradox. So just keep that in mind. But you can read it, or you can look at my description. So here's the deal: we have a example of a muon. V sub mu is equal to 0.60C, which is, I think you can see that's approximately about 1.80 times 10 to the 8th meters per second. And it has a lifetime approximately equal to 2.20 time, or it's microseconds. So I'm just going to write times 10 to the -6 seconds. So that's the lifetime. What I want to find is how long it lives in the rest in the laboratory frame. So how long will the mu particle, the muon, live in the lab frame? That's A. And part B, how far could it travel? Okay, so here's our solution. So the events here, it helps to think in terms of relativity, to think what is the actual event? Well, in this case, a muon is created, therefore its life clock starts ticking, and then a muon disappears. It disintegrates into some other particles That's the second event, and that's supposed to happen 2.2 microseconds. Well, the particle itself, you can imagine maybe it's a who living on the particle, like Horton hears a who or whatever. But the main thing is you're going to imagine it has some kind of conscience or ability to see or think or something like that. But the main thing is the muon sees its existence, both its creation and its death, happening in the same place. Therefore, it sees the two events happening in the same place. Therefore, the muon measures proper time. So muon measures proper time, which is delta t0 equals 2.2 times 10 to the 2.20 times 10 to the negative 6 seconds. So delta t, which is gamma delta t0, is equal to 2.20 times 10 to the negative 6 seconds over the square root of 1 minus 1.80 times 10 to the 8th meters per second over 3.00 times 10 to the 8th meters per second. And then these quantities, of course, have to be divided and squared. So we're going to get 1.8 divided by 3.0 squared. That gives me 0.2. 1 minus 0.2 gives me 0.8. The square root of 0.8 gives me 0.8944. This is going to be 0.8944.
Professor, is that a
Yes.
3 on the bottom? 3 times 10 to the 8th?
Yes, sir.
Where does that come from?
That's the speed of light to that many sig figs.
Okay.
Let me clear that up too. Yeah, so they gave us 3 sig figs. So I said, no sense in using that whole 299,792, so on and so forth. So might as well use that. So I'm going to say 2.2 exponent negative 6 divided by 0.84 or 8944 gives me 2.45 or 2.46 times 10 to the negative 6 seconds. So we see in our laboratory frame, it's going to appear that the muon lives longer. Well, how far does it travel? Well, it travels. So that was part A. Oops, wrong color. That was part A. For part B, the distance traveled, g, is equal to velocity times time. Well, that's going to be 1.80 times 10 to the 8th meters per second times the time, which would be 2.46. I'll carry one extra sig fig here. This is actually 459.7 times 10 to the negative 6 seconds. Not going to waste time doing that color. Okay. So I'm going to say this times 1.8 e to the 8th gives me 442.7. That's good enough. 0.7 meters. So that's how far it would exist, or how far it would go while still existing in the laboratory frame. And the reason that's relevant is when those muons are created in the upper atmosphere, they're created with a speed that's not quite fast enough for them to reach the surface of the Earth, yet we detect them at the surface of the Earth. So that seems like a bit of a conundrum. But when Einstein comes on the stage and offers this new time dilation, we now, as people watching the muon live, see that, oh, wait a second, yes, its half-life or its lifetime is 2.2 microseconds. And if I multiply that times the velocity, I get a distance that's smaller than the thickness of our atmosphere, so it should make it. But from our perspective, that thing's moving, so I know its clock is going to run slow. I can calculate the actual time as opposed to the proper time and get a much larger time. And when I multiply that times the speed that it had, I get a distance that's bigger than the thickness of the atmosphere. That explains to us on Earth why the muon makes it to the surface of the Earth. But you can't just get away with that. You also got to show that the muon itself agrees that it makes it to the surface of the Earth. Can anybody think of what we could do to understand why the muon makes it? Because in the muon's frame, it only lives 2.2 times 10 to the negative 6 microseconds, and it's only traveling at 1.80 times 10 to the 8 meters per second. The muon agrees that the Earth is moving towards it at 1.8 times 10 to the 8th meters per second, and that its life is 2.2 times 10 to the negative 6 seconds. So why does the muon think it made it to the surface of the Earth? Anyone? Well, remember speed, which in this case, I'm talking about the speed of light, is distance divided by time. And I just showed you a way in which the time can be altered. If the time can be altered, does something else have to be altered since the speed of light's always the same? So the muon sees the Earth's atmosphere contracted. So L is going to be, let's say the Earth's atmosphere is 200 kilometers. So it's going to be 200 kilometers over gamma. So that's going to be basically 0.8944 times 200. It sees it as only 179 meters. So that's why the muon believes it made it. So length contraction and time dilation have to be there, because if the c, which is the speed of light, is always the distance traveled divided by the time taken, if you screw up one of them, like the time, then you also have to screw up the other one, like the length. And that's why the two explain it. I'm going to give you some links to other problems to be seen, but this is how you get started. I would definitely look at one for the addition of velocities. You can look at the derivations if you want. That's not quite as relevant unless you just want to understand, but it's surprisingly easy what you do to derive them yourself, because it's all just algebra. You really don't need calculus for this. But anyways, time's up, folks. You're free to go, and I will see you next class. And I'll wait for the last person to leave before I split.
Mr. Younger,
Yeah.
will you be in your office in the morning on Wednesday?
Yes, I will be there Wednesday.
Okay.
Yeah.
I was just wanting to make sure.
Oh, that's right. Yeah, I had to miss today, so you probably came in and didn't see me. Yeah, I was a little sick, so I've stuck around here and tried to make up other stuff for you guys to do. But yeah, I wasn't there much today. Sorry about that.
No, it's okay. I hope you feel better.
Thank you. Yeah, have a good one.
Okay. Have a good day.
Anybody else have any questions? Mariana, Randall, Gavin, Alex, Didio. All right, well, let me stop sharing. I would go through and look over the other examples, those of you in my class, that your book offers. Those are more in line with what we'll be asking on the tests and stuff of that sort. So please do that. Like I said, you are free to go. It seems like no one else has any questions. I'm not seeing anything coming up on the chat, so I guess I'll go ahead and sign out. But yes, by all means, make sure you can understand and perform all the examples in chapter 36 of your textbook. Of course, there's ones related to the Doppler effect. I'm not covering that in the test. However, you might see it in your homework. You might see it in your practice test. Just know it's not necessary for your test, your online test, or your final exam. So have a good one, folks. Bye-bye.